I have this function in red coming through. So it looks like somebody saying that the limit as x goes to a is L. L is right here. You guys see that? So let me show you the first picture because I wish they put both of these together. So there's L. Okay. So look at these boxes that's happening. So here's the idea. If the limit of this function as I approach A is L, then somebody should be able to give me any distance away from L. So this is what we call epsilon. So somebody should be able to give me any number they want to here, which talks about how far away from L I am, and I have to always be able to find a region around A that goes there. So if somebody's like, no, I want from here to here. Well, then can't I find a little region that always goes there? If they make epsilon smaller and smaller and smaller, I can always find a region that lives in the little box. So they set up this big blue box, and I go, here, this box always lives in there. All the outputs are in there. And no matter how small they make epsilon, if that really is the limit, I can always do it. Now, what if I thought the limit was here? Once I go here, once I get really shrunken down in here, do you guys see that? Then I'm never going to be able to get in that box. What's a good way to show this? Well, they get a little tighter there, but if I thought the limit was here, right? Which means then I'd have to, if I got really close to it, you see how this would be here. It wouldn't contain this dot anymore. It wouldn't be a box that contains a dot, so it wouldn't work. If I had the limit wrong, I could find an epsilon where eventually it wouldn't be in there. Maybe. So what am I going to, I want to see what happens when epsilon gets really, really tiny. I want to let epsilon go to 0, basically, almost. Right? You see that come off. I put that mark there forever. Okay, good. So, let me give you this, and then we'll talk about this. So here's the formalization of what we were just saying, right here next to the picture. So somebody comes along and says, oh yeah, you think the limit is L. All right. So I'm going to give you some epsilon, like some really tiny epsilon. And then if the limit really is L, I always have to come back at them with a delta. So epsilon is on the y-axis. It's the distance away from L on the y-axis. Delta is on the x-axis. This is kind of tiny, but it's A minus delta, A plus delta. This little region there. I like it. So if that really is the limit, it shouldn't matter how small this dude comes at me with epsilon. I should always be able to find a region, a delta, so that I'm always within there, around what I think the limit is. Now that's a lot of formalization of an idea that isn't that crazy hard, but it's kind of like the groundwork for defining distance in a lot of different theorems. You see epsilon and delta everywhere. That's why I don't like to skip this section. In English, this says that if L is the number that f of x approaches, then we should be able to find an interval around A where all the outputs for the inputs in the interval are arbitrarily close to L, defined by epsilon. So somebody gives me an epsilon, I should be able to find a region around A where it's always that close. The outputs are always that close. If I thought the limit was here, I'm already wrong. But if I thought the limit was here, then it looks good right now, right? If I thought the limit was right there at the top of this box. It looks good. But what's true about epsilon? It can get as small as it wants to. So then somebody just makes it smaller, and then I'm screwed. So if my guess for the limit is wrong, this process will quickly show me that I'm wrong.
How do you know when it's right?
We'll see that too. It'll be the proof that it's right. I like it. So this is your first, very often this is your first foray into proof writing. Right? I understand that sounds painful, but it's a very baby step. It doesn't get too freaky. It feels like you're cheating in one place, but it's what's called a construction proof. We're going to construct a delta. Somebody's going to give us an epsilon, and we're going to construct a delta that does what it's supposed to do. Okay, I like it. Let's look at like a concrete example of this. So I can hear in your brains, you're all like, give me numbers. If I look at this one, I love these kind of problems here. Can somebody tell me what the value of epsilon is for this problem? Maybe look at the handout I gave you. What did somebody assign to epsilon? What value did somebody assign to epsilon? Which one of these deals with the outputs? 0.2. 0.2 is epsilon. I think the limit is 1. So somebody can tell me, all right, let me get 0.2 away from 1. So if I'm 0.2 away from 1, you guys see that? There you go. Bam! Concrete. Kick ass. Concrete. Awesome. Not every problem's going to be concrete because this is still a theorem, right? If I get within 0.2, can you guys see how I can find this region on the x-axis that lives in there? So where's 1.2 go? Right here. It goes back to 0.7. Where's 0.8 come from? It comes from 1.1. Now, here's the trick. All right. Really? So how did I get those things? I just went 0.2 away from 1, and then I saw where 1.2 came from, and I saw where 0.8 came from. So that's the region that works. Now, but what am I going to let delta be? How far away from 1 do I want to get? So what's the options for delta? How far away is this? 0.3. 0.3. And how far away is this? 0.1. So if I let delta be 0.3, I'm going to go from out there, and then I'm going to also go up to 1.3. Does that work? Because wouldn't this side be out? Right? Actually, it would be, if it kept going, it'd be out down here. So you always pick the smaller one. I'm going to let delta be 0.1, because then if we go down, it's definitely contained in there. It's definitely contained. Maybe. This is the visual of this. So if somebody gives me some epsilon, I always have to be able to find a value for delta so that all the outputs between there is going to be contained in here. If the limit is wrong, if my guess for the limit is wrong, that won't happen. For some value of epsilon, I'm eventually going to get out of there. Okay, maybe. Slightly different way to look. This comes up later in this class, but let me give you another idea. In pre-calculus, you see these horizontal asymptotes, right? If I had a horizontal asymptote at y equals 3, what does that mean? You guys remember? Yes?
It'll get really, really close to 3.
Beautiful. Do you see that? Already in pre-calculus, you were saying the language that we're finally defining a little bit better. So what this really means is, it can't always just be wherever it wants to be. If the limit is 3, there has to be some point after which it never gets further away. It always gets closer and closer, right? There's got to be a point. If there is absolutely no point where it just stays a certain distance away, then that is not the limit. It can't be. If that really is the limit, it eventually has to get closer and closer, arbitrarily close. I could use epsilon and delta for this shit, right, to define what the distances are. I like it. So a limit at a point instead of at infinity has to work, however small I make this region, I have to always live inside of that region if that really is the limit. Okay, so what does this mean for us in a problem that doesn't have numbers for us? Let me give you one more example that you can use your graphing calculator for, because you're going to have to do this in your homework. Let me see if I can find one. I don't remember what I assigned. inflate it and assign number 8. Number 5, let's do number 5. So there's number 5. It's got a little picture of a graph on there. That means use your graphing calculator. So let's see. Let's do a little bit of side work here. So it says if x minus pi over 4 is less than delta, then absolute the tangent of x minus 1 less than 0.2. I like it. So looking back here, what are these red lines? They're just the values around there. So here, what is epsilon in this problem? What's epsilon? 0.2. I love it. How did you tell? Well, one thing is, that's frickin' delta. This is the function that we're talking about, so this must be the epsilon. Epsilon is always on the y-axis. I like it. Epsilon's 0.2. So to think about this, what's the limit? What's the supposed limit? Oops. I didn't say zoom in. No. What's pi over 4? That's on the x-axis, right? So what does this say? As I get really close to pi over 4 for my inputs, as x gets really close to pi over 4, what are the outputs doing? Getting really close to? No? This is the distance away, right? So let's go back. Let's remember how do I say this? What does this mean? What does that mean? What does absolute value mean? What does it mean? Why is it always positive or 0? Because what does it physically mean? Distance away. Beautiful. If you didn't know that, this is bad. So absolute value means distance away. Right? So this is all the x values that are 2 away from 1. That's what this means. This is the difference between a number and 1. And I want that to be 2. I want the distance between a number and 1 to be 2. So that would be 3 and negative 1. All right, maybe. All right. So I want the distance between the function and 1 to be less than 0.2.
1.2.
Then you could, all right, and then you could figure out, so it's going to be 1.2, and what's going to be on this side? 0.8, same way as that last problem, right? But it's not always going to be that. So what's right in the freaking middle? 1. Right. How do I know that? Because what is the form of this? F of x minus L, less than epsilon. That's the form of this. So how do you tell what L is? Well, you just look at what's in the right place for L. What do I want this function to do? I want it to get 0.2 away from 1. So that's what I think the limit is. Okay. All right. And what's this guy? This is the x minus a less than delta. So the value that I'm getting really close to is pi over 4. So what's my function that we're dealing with? So where does it show up? Function I'm dealing with is tangent. Okay. So this is all x shit. So this has got to be all output stuff. So this is the function I'm working with. I want it to, in fact, what is tangent of pi over 4? What's tangent of pi over 4?
1.
It is 1. So that limit is correct. So this should kind of work out nice, visually and for the problem. Right? So this is what that means. I should be able to get as close to 1 as I want to. In fact, I can get within 0.2. Of course I can, because 1 is the limit. If 1 is the limit, then I don't care. I should be able to find some distance away from x where I'm always this close to 1. What if somebody makes it closer? It'll still work, because the limit is 1. If you make this basically 0, I can just make it equal to that, because that's what it is. The limit is 1. Okay, so how do I recreate? So this kind of problem right here is asking you to recreate this for yourself, because this was relatively easy. So I want to recreate this. So what's the function I'm dealing with? Tangent x. Take a quick second, make sure I'm in the right mode. Always a good idea. And what else do I want to show up? So I'm gonna graph tangent x. I'm gonna have that show up, and I also want 1.2 and 0.8 to show up. Okay, I like that. So let's see what this looks like so far. Oh, quit. Oh, I got stat stuff going on. Let me turn this off. Now I'm all freaky. Freaky window. What do you do when you have a freaky window? When you don't see anything. What do you do? Anybody know? Yeah. Zoom 6 to get to a standard window. So there's tangent. And then here comes there's my lower part. And my upper part's going to be really close to that, right? And you guys can already see this kind of looks just like that picture if I zoom in a bit on this. One of my favorite things on the graphing calculator is zoom box. It's kind of like enhance all the stupid CSI shows. But I can do, zoom box. I don't know if you guys ever have done this. I can zoom in a little bit over here so I can see that axis. Enter, and then you drop it down and over, and it opens this box. That looks pretty good right there. Sweet. Bam! There's the function. There's that guy. There's that guy. So what is it that I need to find? So somebody comes at me with epsilon. Which axis does epsilon relate to? The y-axis is all about how far away from that limit somebody wants me to get within, right? That's what epsilon is. So what do I need to find out in response? How far away from x, which is the delta. So can you guys already see? Can you drop down? Well, where do I want to go then on the x-axis? I want to go whatever the shit that is, and whatever the shit that is. That would be my little window on the x-axis. And then what's my delta going to be? The smaller distance away from pi over 4. Just to make sure the whole thing fits. I don't want to go outside the box. I got to stay in the box. So how in the hell do I figure out what the x value is right there? Anybody know? Or there, for that matter. They're both the same way. How much of you guys use the TI? What do I want to find between these functions? What do I want to find between this function and this function? I want to find the intersection. And I want to calculate. I want the calculator to freaking calculate it for me. So this whole top row is all about graphing. So look at that one that says calc. That sounds like it might be a good place. So go second, trace, and of course you see what we want. The intersection. So it's going to ask you 3 questions. Right? What is your name? What is your quest? It's going to ask you, there you go. So here's the shortcut for all this shit. You ready? If you hit enter right now, it will automatically bounce to the next curve. So then I can just go to the intersection. So see how it said first curve? That's that first little cursor thing, right? I just hit enter and it's okay, this is the first curve. Second curve, all right. I'm going to hit enter. The third question is going to be guess. So I might as well just go right on top of the damn thing. That's my second curve, and what's my guess? Right there. So that's the intersection. What's encouraging here is I get y equal 1.2. That's what that should be, the top one, right? But this is a value on the x-axis. That's a 0.876 right there. All right, so here this will be kind of recreate this a little bit. Shoo! That's should be right there. I'll just make it big. So this will be plot 0.876, and now I want to figure out this. Ooh, that's the wrong one. So plot 0.876. Now I want to figure out this other guy the same way. Do the intersection. Enter. That's the wrong function, so I'm just going to hit the down arrow to get to the next function. Should be right. Let's see. 6747, sure. So the answer to this question is going to be a value for delta. So somebody gave me the challenge. Okay, I'm going to let you go 0.2 away from the limit. Can you find a region on your x-axis that always contains that, that's within that box I've set up? So that's why we figure out one side, the other side. What's delta going to be though? Which one is, what's the distance here? You can't do it in your head too easy if you're trying to do that. Well, apparently I'm going to try.
Is it too lazy to just say 0.876 minus 5/4?
No, holy shit, do that, because that's exactly what you should do. Yeah. What is that? What's 0.876 minus pi over 4? 0906, okay. And what's pi over 4 minus 0.6747? I'm finding the distance away, right? So I want delta to be the smaller one, so I always live inside the thing I want. 1113. So to be honest, your delta can just be 0.09. Any number that's smaller than both of these. You can just pick this number, or you can make it a number smaller than this. You're golden. I like it. Okay. So I'm going to let delta be 0.09. Some small, so that I'm always inside that region they set up as my challenge. All right, so that's one level to this, is the visual level. The next level is the proof, the actual writing of the proof. This thing is too specific. This gives me an actual value of epsilon. I got to do a proof for any value anybody gives me. Anything they want to do. 0.1, 0.001, whatever. Okay. Let's see what that's going to look like. I have an example on that sheet, but let's do one together. Let's take one right out of the book here. Let's do, really doesn't matter. Let's just do that first one, it looks like. I don't think I signed this one. Okay. So number 19, prove this statement. First off, just make sure it actually makes sense, right? Especially this one that I made up. Is that true? Yes. So on one level, you should be over this shit though. Don't just say, well, why would I do any of this shit? Because I can see that's the limit. Well, the whole purpose of this is getting used to the setup of this proof. The really bad thing about this is most of the ones we're going to work with are going to be linear. The minute I make them quadratic or something else, the level of difficulty goes like way up. It's insane. So it's either going to be a little too easy or way crazy hard. So I go for the little too easy so you can get used to the process. Identify a few things for me. What's f of x? Yeah, 2 plus 4x over 3. What's a? 1. That's the value that I want to get close to.